Okay, so we have looked a little bit at what is AI, what is intelligence. We have looked at a little bit of history, which saw how this quest for building intelligent machines has been around for at least a few hundred years. Now, let's catch up with what's happening in the real modern times, so to speak, as to when this field of AI has evolved essentially. So, the cast of characters that we have seen so far, they go back to 1300 AD, where we talked about Jaeza and what Ramon Lull tried to build, and then various people along the way essentially. Let us first now look at how AI got its name essentially. It is largely credited to John McCarthy, who along with Marvin Minsky and Claude Shannon organized what is known as the Dartmouth Conference in 1956. In fact, 50 years later, they had another conference at Dartmouth. Just to recap, do a study of what has happened since the first conference. And Marvin Minsky and John McCarthy. John McCarthy is the one who is credited with choosing the name artificial intelligence. There are various people who have objections to the name artificial intelligence. Some people don't like the fact that we use artificial there. Some people say computational intelligence. Some people say that why do we even call it intelligence? Why don't you call it heuristic programming or something like that, or smart machines or something like that. But anyway, the name artificial intelligence has stuck, and it's John McCarthy who gets the credit for naming it in this conference, which was organized in Dartmouth College in 1956. And the idea behind the conference was a 2-month 10-man study of artificial intelligence. That's where the name came in, on the basis of the conjecture that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. That is the basic idea behind AI, that whatever problem solving we do, we can describe it in so much detail that we can make the machine do it essentially. Of course, that is in some sense what we do in programming also. If you write a program to, let us say, invert a matrix, then you are basically writing down the steps that you would do it, and then the machine can repeat it many other times. And this basically the AI idea of AI is that we can write programs which can solve whole classes of problems, and we will see what is this notion of general purpose problem solvers as we go along in the course. And there is a good description of the Dartmouth conference in this book by Pamela McCorduck, in this book Machines Who Think, we had mentioned earlier. So, who are the people who organized the conference? The first was John McCarthy. He was the driving force behind this. That time he was an assistant professor at Dartmouth, and he was also known for designing the Lisp programming language, which for many years was considered to be the language for AI. He also worked on logic and common sense reasoning. Then there was Marvin Minsky. He was then a junior fellow at Harvard. Later on, he became a professor at MIT, and he died quite recently in 2016. Became one of the most influential figures in AI. They co-founded the MIT AI lab, and he is known for his ideas on frame systems, which is the foundation of object-oriented programming. And he wrote a book called The Society of the Mind, and more recently he wrote a book called The Emotion Machine essentially. Then there was Nathaniel Rochester, a young engineer at IBM. He designed the IBM 701 and wrote the first assembler for that machine. He supervised Arthur Samuel, who we will briefly mention again, who wrote a checkers playing program. It is said that the marketing people at IBM reported that people were frightened of electronic brains, resulting in IBM stopping work on AI. And this happened because of Arthur Samuel, because he wrote this program which could play checkers. And not only could it play checkers, it had a learning component built into it, and it could eventually beat Samuel. So, this whole Frankenstein kind of image was created that AI will destroy us, and more recently also people have been talking about that uh, that that AI will take over humankind, and there is some singularity point, and some very fanciful ideas. Then there was Claude Shannon, who we know as the father of information theory, the notion of entropy and things like that. He was a mathematician at Bell Labs, and he hired McCarthy and Minsky for summer when they were graduate students. But the show stealers in Dartmouth, according to McCorduck in her book, she says that were Herbert Simon and Allen Newell, two vaguely known persons working at Carnegie Tech. At that time, Carnegie Mellon University was not there, and there was this Carnegie Tech, which eventually evolved into the university, and Rand, who were also invited to Dartmouth Conference, and she says almost as an afterthought. But they were the real show stealers. So, along with J.C. Shaw, who was also from Rand, they had already developed a program called Logic Theorist, LT. It was the first program deliberately engineered to mimic the problem solving skills of a human being. It went on to prove several theorems in Russell and Whitehead's celebrated Principia Mathematica, finding shorter and more elegant proofs for some essentially. And there is some story that the Journal of Symbolic Logic refused to accept a proof co-authored by a paper, but we are not sure whether that's true or not. So, these are the two persons who were really the show stealers at Dartmouth. Simon was an American political scientist, economist, sociologist, psychologist, and a professor, most notably at CMU later, whose research ranged across the fields of cognitive psychology, cognitive science, computer science, public administration, economics, management, philosophy of science, sociology, political science. As you can see, he is a very diverse, he had very diverse interests. So, he also won a Nobel Prize in economics, this thing. Allen Newell was his PhD student actually, and was a long term collaborator, and he designed this language called IPL, Information Processing Language, in which the program LT or Logic Theorist was implemented. So, the information processing view of AI that we have put forward comes to us from Simon and Newell. They became leading figures in AI at CMU. They wrote a program called General Problem Solver, which was a pioneer in the use of heuristics in search, and that is something that we will be doing a lot in this course, and adopting the human like approach, which they call as mean sense analysis, which we will briefly look at later. Their work defined the information processing view of AI. One shining example which came out of CMU was this program called SOAR, which you can still download nowadays, written by John Laird, and it is a cognitive architecture in which you can plug in your information or knowledge, and it can do reasoning for you. Simon and Newell gave us this idea of physical symbol systems. So, symbol we have already said is a perceptible something that stands for something else. So, alphabet symbols, numerals, road signs, musical notation, everything is a symbol. A symbol system is a collection of symbols or a pattern of symbols. So, words for example are made up of different alphabets, arrays, lists, or even a musical tune can be thought of as a symbol system. When they say physical, what they mean is something which obeys laws of some kind essentially. So, just like the physical world obeys the laws of physics, their symbol systems would obey some laws of some formal systems. So, long division, abacus and algorithm and so on. They gave us this hypothesis. I mean, you cannot, it is only a hypothesis that is what we assume is true. They say that a physical symbol system, as we have just defined, has a necessary and sufficient means for general intelligent action essentially. So, what they are saying essentially is that you can write programs which are basically symbol systems, because you choose a language and you write code and stuff like that, and he said that programming is enough to create intelligent systems. This ability to manipulate symbols is sometimes called symbolic AI and or classical AI. Haugeland calls it the old fashioned AI. This is in contrast to machine learning, for example. We have seen very briefly in the introduction that a neural network stores information in the form of weights in connections, whereas they are not explicit, that the neural network knows that it is looking at a horse or a cabbage or whatever, because the weights somehow have this information at, some people call it as a sub symbolic level. Whereas classical AI is composed is concerned with symbols which stand for something explicitly, and in some sense it is a good old fashioned AI essentially. So, when we talk about symbols, we can go back to the time before Descartes and everyone, where there was no notion of the mind as all. You simply saw the world and you believe that what you are seeing in the world is what is out there. So, it was Nicholas Copernicus who kind of, according to Haugeland, put the first wedge between thought and reality essentially, because he showed to us that it is not that the sun which goes around the earth. When we see the sun, we see it rising in the east and setting in the sun, and we feel, or the geocentric model of the earth was, of the universe was, that the earth is at the center of the universe and the heavens are going around it essentially. But it was Copernicus who said that it is the rotating earth that creates the illusion of the sun, the moon and the stars moving in the sky. So, for the very first time in at least Western human history, we could see that what you are seeing is not what really is out there essentially. So, when we talk of reality, we can ask, what is really out there? What is objective reality? And one thing is clear, that everything in the physical world is made up of a small number of fundamental particles. So, we are talking about physics and science here. Even though we do not quite know what those fundamental particles are, some people say string theory, some people say other stuff, quarks and whatnot. But we agree that the whole universe is made up of fundamental particles, unless of course one were to believe that there is no matter, but there is only energy or idealism. But the laws of physics that explain the behavior of these particles are sufficient to explain the behavior of ensembles of such particles. But the problem lies in the fact that a human adult, for example, is made up of 10 raised to 27 different atoms. I mean, we are not even going to subatomic level here, we are talking about atoms, and these atoms continuously interact with zillions of surrounding atoms all the time. The air we breathe, the food we eat, the vibrations of air molecules we sense as sound, the impinged upon by trillions of photons which have momentum but no mass. So, there is lots of going on at the physical level. Can we even hope to write down equations for these and solve them, 10 raised to 27 atoms? And what would we get if we did solve them? A prediction of their location and movement? How will that help? So, basically we are saying is that human beings model the world, we see the world, we understand the world, but really the world is made up of some very fundamental particles. We do not see it like that. So, it is a world in our minds that we see. The world around us, including us, operates according to the, and in principle be explained by fundamental laws of physics, nothing else is needed. But we, the thinking creatures, can create our own worlds in our own minds. It is only our creation that is meaningful to us. The fact that you are looking at a tree or a cloud or a chair is in our heads essentially. This is an extension of the idea what Galileo said, that things are happening in our heads. And if you have seen films like The Matrix or Inception, you can see that in Matrix, for example, the main character Neo imagines that he is a software engineer in New York, whereas he is a captive of some robot on some spaceship somewhere essentially. So in his mind he is in New York, but in reality he is not. So there is a very interesting site called The Powers of 10. It's a film that I would recommend everyone to have a look at. It's basically a film in which they start with a picture and then they zoom out 10 times in every new frame essentially. So, first you see something, then you zoom out, you see something which is 10 into 10 times, 100 times bigger and so on essentially. And that gives us a feeling of what the world is like. So, if you look at objects which are about 1 meter in size, a typical door or table, the height of a child is something that we can perceive. Objects about 10 meters, the width of a road, a small house, a tree, 100 meters, a sprint track, a meadow, a pond, a skyscraper, 1 kilometer, the size of, for example, the Golden Gate Bridge, 10 kilometers, the diameter of a small town, 100 kilometers, the distance from Mandi to Manali, 10 raised to 6 meters, the distance from Chennai to Pune, for example, 10 raised to 7 meters, the diameter of the earth, which is about 12,000 kilometers, 10 raised to 8 meters, the diameter of Jupiter, 10 raised to 11 meters. We have skipped a few things there. The distance from Earth to Sun, Saturn to Sun, solar system, and so on and so forth. So you can go, 10 raised to 26 meters, the visible universe essentially. So more recently, we have been receiving images from the James Webb telescope, which are apparently going very far back into time and very far away into time, into space. Sorry, very far away into space and very far back into time. So this is as we are zooming out, from 1 meter to 10 meters to 100 meters and so on, you go out and eventually you see the whole universe. You can zoom in also. If you go to 10 centimeters, then you have small birds like a sunbird or a mango or a cell phone, or 1 millimeter, a mustard seed, 100 micrometers, maybe a pollen grain, 10 raised to minus 5, a bacterium, then a virus, and so on, the structure of DNA, carbon's outer shell, proton, quarks, gluons. So, there is this whole range at which things exist in the universe essentially, and this Powers of 10 is a nice film that you can watch essentially, which illustrates this. At both extremes, basically what you see is something like a collection of random particles, whether it's galaxies or whether it's subatomic particles. They look very similar, but in between we have these different concepts. Our perceptible universe for us humans is something from, we can see a pollen grain at 10 raised to minus 4 meters, or we can see things like the Golden Gate with 1 kilometer, or maybe you can see a mountain range which is 10 kilometers and things like that. But it's very limited essentially. The rest of our knowledge about the world comes from science in some way. Scientific progress enables us to extend our concepts and distinct different scales. So, the domains of our reasoning, we are talking about representations, symbolic representations of the world. So, we already said that while the real world that we want to reason about is indeed made up of collections of fundamental particles, those fundamental particles, whatever they are, cannot be the elements of the domain. We can't represent the world in terms of those fundamental particles that we would use for representation and reasoning. This is simply because there are far too many of them, even to, for example, to describe a grain of rice. Instead, depending upon the focus of study, we can represent atoms or molecules, biological cells, animal organs, living creatures, societies of living creatures and so on. We create our own levels of representation essentially. These are all in our minds. So, what we are saying is that fundamentally, there are all these fundamental particles which for some reason stick together. So, something we see as a human being, something we see as a tree and so on, but we see them as human beings and trees. But at a very fundamental level, they are just particles sticking together. every domain of study defines its own what we call as an ontology essentially. So, if you are looking at knowledge representation, we often talk about an ontology. So, if you look at this domains that we saw, you can see that there are various fields of studies: cosmology, astronomy, astrophysics, geography, geology, Newtonian physics, biology, cellular biology. Every discipline creates its own vocabulary, which we can say is its own ontology. So, every discipline creates its own representations, and in that sense, when we represent the world, our representations are dictated by the fact as to what is it we want to do with the representations. So, we want to reason with them at some level of detail. So, a cell biologist would talk of a different level of detail, and economists would talk of societies and things like that. So, we create our own representations, and that is the thing that we must remember when we want machines to be able to represent about what the domain they are operating in essentially. So, we will stop here, and next we will look at this idea of problem solving that we want to capture in this course, in particular one approach to problem solving, which is search methods. So, we will take that up next.